I want to give you some basic rules and information regarding double integrals and iterated integrals just over rectangular regions. So first, some rules. Basically, the principle here is to proceed one variable at a time. Here is a sample iterated integral. Notice how my integrand here is actually a function of two variables. We might say z equals f of x comma y. I have two differentials here, dy and dx, and I have two integral symbols with two sets of limits. Now, the rule here is to work from the inside out, one variable at a time. The inside set of limits must go with the inside differential. So the -1 and 2 must correspond to y, and the 0 and 1 must correspond to x. That will always be true. So what I can do is I can copy that integral symbol with the 0, 1 and copy the dx without changing them, and only work with the stuff inside the green brackets. Next, I need to take the antiderivative of 2xy, right? So the secret here is to treat y like a variable and treat x like a number. And so what works here is the reverse power rule. It becomes x times y squared. X is being treated just like if there were a 3 there. No problems. So next, what I'm going to do is the substitution. I'm substituting the 2 and the -1 for y, not x, and I'm going to subtract. I get x times 4 minus x times 1. That simplifies, and you can see that the integral is now going to be of 3x dx, and that is very easy to do. I get 3 over 2x squared, and I substitute the integral is equal to 3/2. Now I'm going to say a few things about notation. This is the general notation for a double integral over the region R, differential dA. The R, in general, it's any region. For the purposes of this lab, it's a rectangular region. We'll denote it like this, interval cross interval. The AB corresponds to the x's, CD corresponds to the y's. dA is a two-dimensional differential, and it corresponds exactly to the dx when we're doing one-dimensional integrals. You can think of it as a little teeny tiny rectangle in when you're expressing this integral as a Riemann sum. Here's something cool. You can always do a double integral by expressing it as an iterated integral and following the rules that were on the previous slide. And so you can always do this. So I think it's important to mention that when you have this notation with the two integral symbols and the r and the dA, this is a double integral, not an iterated integral. And when you rewrite it with all of the numbers included in the limits here, and the dy and dx separated over here, this is considered an iterated integral. Technically, they are two different objects, but there's a theorem that says, look, if you have a rectangular region, you can always do a double integral as an iterated integral. That makes these problems easier to do. Here's another cool fact. You get to pick the order in which you do these integrals. Can you see the difference here? Instead of the CD being on the inside, they are now on the outside. Instead of the AB being on the outside, now it's on the inside. I've even switched the dy and the dx so that AB still corresponds to dx. This was proved by Fubini back in the day, and it's very useful to us. It means it doesn't matter what order we do these single integrals in. You always get to pick. So here's an example. I want to compute this double integral, and I have this rectangular region. So my first step will be to express this double integral as an iterated integral. And for no particular reason, I am choosing to integrate with respect to x first. I don't think either way is going to be easier. The next step is to find the antiderivative. Now, it's the antiderivative with respect to x, and because there's something complicated inside of the sine function, I need to do a substitution, u equals 2x minus y. Something slightly tricky is that to find du, you need to take the derivative with respect to x. Everything is with respect to x right now. And that means that du is equal to 2 times dx. That y is being treated like a number. So I do that substitution, I find the antiderivative, and I get a cosine function when I'm done. And I can make those substitutions of pi over 4 and 0 for x, and I get this function. It's an integral with respect to y now. Something I'm going to do to simplify this is not only cancel those two negatives and turn them into a positive, but I'm actually going to apply a trig identity to this expression and this expression. Cos of pi over 2 minus y is always equal to sine of y, and cosine is symmetric with respect to the y-axis, which means cos of negative y is cos of y. This makes this integral a complete joke, and so the integral is equal to 1/2 plus radical 3 over 4.